As said, Mika Eronen, and coming from Safety Class Experts. We are a Finnish expert services firm working globally, providing expert services, non-material expert services, training, consulting, advisory, diagnostics for 3 different customer segments. First priority, of course, is the glass manufacturers, and the second priority is the vehicle manufacturers of various kinds, and then the last one is the glass processing equipment manufacturers. We started initially working with the heat treatment processes, which are naturally the most challenging processes when it comes to manufacturing any type of safety glass these days. However, our experience took us further, and now today we are already concentrated to the entire manufacturing chain, starting from the very first stages from cutting until the final inspection. Quality works at the last level before the glass is being shipped to the customer. No matter whether it's bullet-resistant glass, automotive glass such as passenger vehicle or heavy commercial vehicle glass, tempered side lights, backlights, windshields, or architectural glass. This is as long as it's safety glass of some kind, or at least glass. That's where we work with. Okay, enough of that. Let's go to the topic. Now, this is probably the single only presentation not directly related to the automotive industry and the windshield manufacturing processes. And in that sense also a very different presentation to the other ones which I've been seeing during the last couple of days, because I'm perhaps presenting something which is more on the floor level and on the manufacturing floor level and technical manufacturing information. So if there's some information that perhaps I don't get the time to open enough during this 20 minutes, then I'm available for your questions to explain the backgrounds. Anyhow, hopefully you can follow. There's the presentation outline. Firstly, I'll shortly introduce the outline, the challenge itself. Of course, I need to accept that most of you realize already the challenges we are facing on the automotive and the vehicle glazing end when it comes to design properties. Secondly, I will go to a case sample where I show you something what we did actually on the client service end, and how it works and how it goes through. Perhaps some of you, if you're working with windshields, then perhaps you can find some tips there, hopefully, how to get into solving and roll out to the floor level and solve your problems there. Lastly, after the case sample, before the summary and conclusion, I will explain you the process parameters, the key process parameters for those which I've found myself in now perhaps in the last 16-month period in 7-8 different countries. In the cases I've been working, the most important and key figures, key parameters, variables affecting to this optical performance, which is our topic for today. Now, before going to the actual optical defects topic, short summary of the design features the car industry is going into and developing all the time. And first, of course, it's the safety functions in the vehicles. These are many different type of safety functions are increasing all the time, and perhaps we don't always recognize the relationship to the windshield, but there is actually. We could talk another 20 minutes about that separately, but there's a lot of relation to the windshield when it comes to safety, not just the visibility of all the general overall performance, but also the mechanical durability of the windshield, because it's already these days it's an important part of the vehicle. Aerodynamics, of course, we are talking about green values in every aspect of glass manufacturing these days. So aerodynamics is something that is affecting the design and how these car makers are evolving their new models. Driving comfort, of course, again, is a topic. Everybody wants to drive a car that is the most comfortable, and there we see various aspects. And finally, the aesthetics, which is in completely different level than it used to be perhaps another 10 years back. If we then now go deeper into those 4 different characteristics there and design features, we can establish various individual design characteristics, such as, for example, for aerodynamics and efficiency. If we link it now to the optical defect, which I'm going to present you, is the decreasing installation on the vehicle. So we see continuously smaller and smaller installation angles in the vehicles, especially on the passenger car end. The cars, as good examples, for example, PSA group cars, Citroën, Peugeot, they are featuring rather small installation angles, and this is, of course, then makes increasing the complexity of the production. That's a single factor there, and then also the decreasing component weight is something I want to highlight. This is an important factor and will come up later on when we go forward. Since the manufacturers are driven to thinner the solutions, we are now seeing asymmetric, what is called asymmetric class combinations, 1.6, 2.1, 1.8, 2.1, and that's something that requires from SAC bending quite a lot of understanding, and also technology-wise there's certain limitation, you could say. Last but not least, for the 2 topics for the optical defect, and it's the increasing size of the windshields. We've seen that the overall glazed area in vehicles is growing and growing, and this continues to go on in all segments, perhaps excluding the military vehicles, of course, but for the part of passenger vehicles, buses, which are on heavy commercial segments, are seeing more and more glass, and the windshield size are increasing all the time. The last point is which I'm going to highlight for the optical topics, is the higher quality requirements from OEM end. Many customers these days are feeling a rather strong push from the OEM segment to meet more stringent quality requirements, and this is something where perhaps a lot of questions arise. Is our technology in the level to answer all these technical quality requirements that the OEM end is asking for? Now to the case sample and more into the class itself. Optical defects. Now I will be presenting you as a case sample. So before going to the case sample, I'll just draw a little very short and narrow introduction to the different type of optical defects. Basically, you can draw separate the optical quality into 2 different kind of segments. The first one being the transmission optics, of course, and the second one is the reflection optics. Now, transmission optics typically is inspected in the most simple fashion to inspect a transmission optics on any piece of glass is basically using a shadow graph investigation method with any type of light source sufficient enough to provide a good lighting reflected through the glass. Now, in those 3 pictures here, Mr. Toimi. Okay. In these 3 pictures, we can see the couple of samples I've collected for you. Now, on the upper right-hand side, you will see a transmission optics defect called black pitting distortion or spot distortion. There are various names. Perhaps someone else has another name here. So, anyhow, this is one of the kind of defects you often witness in my field of work. Here's a bright pitting distortion. In this picture we see on the left hand side, we see in the center we see slight battering distortion, which is an example, which is an defect that appears in the very close to threshold limit situations. On the bottom end we see two different kind of defects. There's a focal line, burn line, which is caused basically because of the temperature difference between the black enamel, so the printed area, and the clear surface. And there's also a white area there. You could call it some kind of a white line, but it's related to the fact that the shape of the glass is not progressive, but there is a overbend on that particular area. Now then, if you take a look at the reflection optics, on the reflection optics we can use various kind of methods, but these days for car makers perhaps the most interesting ones start to be the TL957 Volkswagen standard, which is stipulating for this grid to be reflected on the surface of the glasses. If I recall correctly, the diameter of the grids is the dimensions of the grids is 30 by 30, and then you look for any deformation of these reflected lines, and this is pretty strict quality inspection for those who know it. The other one here is just one way of just reflecting with fluorescent tubes, reflecting these straight lines in order to see whether the shape is progressive or not, and this is a good example of shape which is definitely not progressive and non-acceptable for OEM. To the case sample. Now, in the case sample, I'm presenting something I did 12 months ago with a client. It was a large multinational manufacturer who was suffering from a pretty bad optical distortion situation. As we see here, it was a bright pitting distortion situation. Amazingly enough, they were suffering from this defect for a 5-year period, scrapping 20 to 30% from the glass of those produced glass from 3 individual models. So everyone here who understands the cost at this stage, well, basically they were throwing them in the final inspection, so the production cost and the cost of this waste was playing a huge role eating the margin of the production, and perhaps in some other location the company might not survive from this kind of losses with normal margin. As we know, the prices are pushed down hardly. Now, we worked there, and I worked there for 10 days, and within the 6 days we managed to find some interesting solutions to this particular problem. Now, this is what I normally follow when I start to solve a bending problem, especially if it's related to optical quality and especially transmission optics. I start following the natural process flow of the glass from the very beginning, and that means that I start with the inspection of the pre-processing, make sure that the pre-processing follows the normal acceptable working practices to ensure that the pitting distortion doesn't come from there. And if there is anything to correct, then we correct this to a degree which is possible by the means of the equipment and available materials. Thereafter follows, of course, the bending process inspections and evaluations. And here we see one thing I did during this particular trial was a data locker equipment using a 6-channel data locker to measure all 4 surfaces of the glass in order to understand what is really happening during the bending. I've said many times to manufacturers of the equipment, and also this is a topic that I talk a lot with my clients, is that we really don't know anything unless we know all the surface temperatures, and yes, it is difficult to measure all the surfaces, especially when it comes to this surface number 1. But it's doable, believe me or not. Anyhow, this was done during the bending process condition measurements, and then also we were inspecting the bending process itself and all the small details there. Finally, after all the inspections and overview, we went to the improvement actions. So basically what we start to do, we re-engineered the mold tooling for those 3 individual models, and then adjusted all the process parameters in order to get a good uniform heating. I'll explain that on the key parameters. Now, as I said in the beginning, the results at the time of my arrival for the last 5-year period were at 20 to 30%. And after the 10-day visit, we on the last few days we did a test batch of 170 pieces of glass for one of these most challenging models, which was on the highest level of scrap. And we reached very good results. As you see here, there's an illustration on the results. So 94% initial improvement. A lot of percent signs there. So forget the second one. There was a final inspection station, and they claimed that 1.8% went to scrap, and then I took this 1.8% to a laboratory, and we inspected against the OEM standard, and every single piece went through the OEM inspection by a neutral objective party. So all in all, 97% improvement from the start point, 30% rejection rate. Now, if you take a look at the other variables here, and perhaps the most interesting figures as well, is we're always thinking of course, the euros here, and one big euro maker here, when we reduce initially this waste, of course we get more capacity for production, and these pieces are not going to scrap. But what we also managed to do, as per to the point number 3, we managed to do a large saving for the manufacturer, because we were able to produce the glass from a cheaper float with maintaining exactly the same quality. Whereas previously they were using and importing a separate float for these difficult models, simply because otherwise they lose even more than 20–30%. So there's a role when it comes to flow glass. Soda lime, the soda content and the iron content in this float, it will affect on this threshold limit, close to threshold point optical distortion cases. So you might get a marginal improvement when you purchase another float, but in this case we return to use that standard float, and cost saving approximately $1 per square meter for all those 3 individual models. And last but not least, from those I will highlight that everything we did there, we did with the existing equipment, and the only change was that we changed the material to a cheaper one that was already in the factory and was previously used. So no investments to expensive equipment, any gear, any kind of. The only investment was for our working time. Now, to the work quality and to the key parameters. If you take a look, we go back and reflect what I just showed you. I start from pre-processing when I start my work in this type of defects. So in this presentation, I will also start showing you the key variables from the pre-processing, and so from the beginning of the process flow. So firstly and foremost, the washing process. The cleanliness of the glass really matters. We've done tests where we found out that Instead of washing once, after washing 2 times, we can reduce certain type of pitting distortion. Even we found a marginal change when we washed the glass 3 times, but not in this case, but generally speaking, this might affect. This separating powdering is of course the second topic. If the separating powder layer is not uniform and it's not of a good quality in terms of the homogeneous particles of this separating powder agent, then there's a high likelihood of seeing pitting distortion, especially with asymmetric glass combinations. The mid-storage condition, this refers to the fact that many don't realize that, especially in hostile environments in terms of the weather, the ambient temperature inside the factories, when the glasses are stored for a prolonged period of time, this separating powders start to accumulate to regions. And when this accumulation takes place, there's a high likelihood of this resulting to a pitting distortion. So if you prolong this and keep the glass waiting on before bending, you will be very likely to see problems. Last, thin and air side orientation. There's a real effect there, and especially on just on the knife edge situation. If possible, changing the orientation might help, because especially if cellulite or superfluous kind of separating agents are used, and you then change the one more thin side to be inwards to the inner layers, this thin side then is more harder, and it will take more from the powder. Now, starting to be over the limit of times. Now, let's go to the temperature in terms of the bending process. Most important things. Firstly is the fact we need to realize infrared radiation is something of a heating of a kind that is limited. It really doesn't heat the glass just as that. In fact, from my reading, the limitation in optimum wavelengths is we heat only 0.1 millimeter of the thickness. And then in addition to the fact that the glass is very poor in thermal conductivity, we can imagine that the temperature difference to the thickness of the glass takes place easy. And when this happens, we will see exactly what I show you there. We will see the bright pitting distortion as per to this case sample, and we will also see this black spot pitting, which is related also to the same fact. Therefore, it is important to see that the glass is heated uniformly from both surfaces, and I refer here to highest limit of 20 Celsius difference between the glass plies. Optimum condition, this is only 5 to 10 Celsius. Now, for this, to create a continuous sagging profile, in order to get a good reflection distortion from the surface, you need to have a high quality mold tooling and well enough fine-tuned infrared radiation heating element configuration for the bending furnace. Summary. Over time, everybody's missing the cocktail. This majority of these optical flaws in transmission and the reflection optics are related really to the special requirements in terms of the glass. Sometimes the furnace is many times the furnaces are limited in terms of what they can handle, especially older furnaces. So a lot of things are dependent on the tooling as well. As I said, the market quality of course is increasing, so there is a mixed conflict of interest there, because the available technology perhaps is slightly following behind, and whereas the designers are going forward faster. The single most important factor, the last point here on this slide, is that we need to produce a heating element configuration and tooling that are such of a kind that they will produce the same shape and the same optical quality cycle after cycle without any adjustments. And this is sometimes the most challenging thing for the manufacturers to do. Now, for just a few words more for the limited heating element power. Now, if you don't have sufficient bottom heating power in your furnace, then the only alternative there is to use extra heating by mold tooling, creating reflection mirrors and different additional tooling. And sometimes for this work, an additional external party can be playing a great role. Time is running out, and I'm missing my cocktail. So here are the references in case you're interested to do more reading. There's a lot of information in these particular articles, and all of them are on the book there. Even more coming up from our Class Expert web store. And I thank you now for your attention and patience. Thank you.